All right, we can go ahead and get started. Got my iPad hooked up here. And today we're going to be talking about more serious things, a few more tests, and then we're going to be talking about power series near the end. So, very first thing I want to talk about is alternating series, right? And an alternating series is kind of written in the form where we've got each term an is defined as -1 to some power of n, could be n plus 1 and minus 1 and plus 3, doesn't matter, and then a bn, where bn's are these positive sequences. So in a sum format, this could look like b1 minus b2 plus b3, and then minus b4, and then so on. And what that is we have the sum from n equals 1 to infinity. And in this case, we've got -1 to the n minus 1, bn. And then it's adding and then subtracting, going back and forth. And this type of series has a few more properties than series that are either all negative or are all positive. A big reason or a big difference of these is that they converge a lot easier as long as the terms are getting smaller. Because now, instead of just adding these things, you're adding and subtracting, so you're converging faster, right? So if it does converge, it's going to get there a lot faster. And that comes to the alternating series test. So the alternating series test, and the conditions for an alternating series to converge are based on two requirements. The first one we have here is that the bn, the sequence bn, is monotonically decreasing, right? So in other words, that bn plus 1 is less than or equal to bn. Second requirement is that the limit as n approaches infinity of bn is 0, right? So with only these two requirements, we can guarantee that an alternating series converges, right? So this is pretty nice. This is pretty lax compared to some of the other kind of series that we've been working with. And when we're looking at some of the other tests as well, this is a lot more straightforward. Like, you don't have to take an integral, you don't have to do any kind of comparisons. As long as the limit goes to 0 and bn is decreasing, then we have a convergent series. Now, remember, this is only for alternating series. So let's take a look at our first example. It's pretty easy. We have n equals 1 to infinity, -1 to the n plus 1 over n, right? And this is a pretty simple one. You can kind of guess that if we look at our conditions, we have to apply them and then figure out if we have a convergent series or not. So first off, alternating, right? We've got -1 to a power of n, right? So to determine if we're decreasing or not, we know that n plus 1 is always greater than n, right? Because n starts at 1, so we're always at positive n's. So we're okay there. Well, what this means is that 1 over n plus 1 is always less than 1 over n, right? So that means that every term is going to be less than the last one, right? So then all we have to do is make sure that the limit is okay. So we have the limit as n versus infinity of 1 over n, and of course, that's 0. So with that, we know that this converges. By the alternating series test. Our second example here is the infinite sum, n equals 0 to infinity. We're going to have a little bit more complicated terms here. So we have negative 1 to the n times n squared over n squared plus 5. All right, so go ahead and work on it for about a minute, and then we'll talk about it. All right, so this one's pretty straightforward. So you see here, let's go ahead and start looking at the limit first. So we have the limit as n approaches infinity, and we've got n squared for n squared plus 5, right? And if taking this limit by dominance of powers, you know that this guy is going to be 1. Well, that doesn't satisfy our above condition here, right? This is not equal to 0. So this is going to, we don't know if this converges or not by the alternating series test. We just know that it's kind of inconclusive. But applying the same kind of premise here, right? We have that if we take the limit as n approaches infinity, negative 1 to the n squared plus 5. So if we do it all together, right? This isn't going to be approaching one number, right? Because of the above not going to 0, right? This guy is going back and forth between something that's kind of approaching 1. So this limit does not exist, right? And by the test by divergence, we know that this is divergent. So we have divergent. Test for divergence, right? Okay, so let's take a look at our last example for applying the alternating series test. We have n equals 0 to infinity, negative 1 to the n minus 3, and then we have a radical n all over n plus 4. Go ahead and take a minute, and then we'll talk about it. Perfect. So let's go ahead and start with the limit again. So we have the limit as n approaches infinity, square root of n over n plus 4. It's also worth talking about this n plus 3 up here, right? This doesn't change the fact that it's alternating because the power is, but if it's positive or negative only depends on if it's odd or even in the exponent, right? We have -1 to something, so that -3 doesn't really matter. It just kind of determines which starts, if it's positive or negative. So for a limit here, we have that if we have dominance of powers, so we know that this is going to go to 0, right? Because the dominant power is on the bottom, so that's growing a lot faster. So now determining if the Bn is decreasing or not, let's go ahead and define a function. Right? So we have f of x, and it's going to be the square root of x plus 4. Now remember, the reason why we're defining a function is if we're going to take a derivative, we can't take the derivative of a sequence. This only exists for whole numbers. So we have to define a function x, f of x. We have our derivative here, and I'll go ahead and just give you guys what this derivative is. This is 4 minus x over 2 square root of x plus 4 squared. Now, we're going to find out when f prime of x is equal to 0. And, or just like a critical point in general, right? So I can say for critical point. So this leaves us with x equal to 0 and plus or minus 4. So notice that we don't really have to worry about the -4 case because the sum starts at 0 and goes up, right? So we only have positive ends. So we don't really have to worry about a -x, right? So if we draw a sign chart here, and we've got 0, and at some point we've got 4 here, and then our f prime, if you plug in some numbers, if you like plug in 1 to this guy, you'll see that you're going to get a positive number, right? Now, if you plug in something greater than 4, you'll see that we're going to get a negative number. So what exactly does this mean? So our function is increasing from 0 to 4 and decreasing from 4 to infinity. So let's kind of break this up. Well, we have our initial sum now, but we're going to break it up into 2 parts. We're going to go from n equals 0 to 4, and we're going to have our sum, and then we're going to add our sum, and we're going to start at 5, right, because we already got the 4th one. This goes to infinity, and it's the same thing. So over here, this is telling us that after 4, this thing is always decreasing. So what does that mean about this sum here? Well, we know that the limit goes to 0, and we know that all the terms now are monotonically decreasing. So that means that this guy in yellow converges. And what can we say about the guy over on the left here? Well, this is only from 0 to 4, right? And there's no problems with any of those terms. They all are defined. So this is finite, right? And if we have a finite plus something that's convergent, which is a finite thing, then this means that the whole series converges by the alternating series test. Okay. So let's kind of move on to a brief topic of alternating series. And we're going to talk about error analysis, right? There's a neat little phenomenon that happens when you're working with alternating series. It's that if you have an alternating series, you can kind of define an error. So we've got the sum from n equals 0 to infinity. And we're going to have -1, n minus 1, and then we're going to have our bn's. We're going to define what this guy converges to, if it converges, to s, right? It's equal to s. So we need two conditions, and of course, they're basically the same. They're saying that we've got some kind of convergent series going on here. Our limit again, the bn, and of course those have to go to 0. So given these two conditions, we can define a remainder, and this remainder is defined as the total sum, so this s, minus the partial sum, this Sm, right? And this can be bounded by bn plus 1. So what exactly does this mean? Because that each term is getting smaller and smaller, we know that the difference in the sum and partial sum has to be less than the next term. So since each term is getting smaller and smaller and smaller, the difference will only change by that much in total. So anything larger than that won't ever get changed by this thing. So let's do an example. So we got number 4 here. And we have that n goes from 1 to infinity, -1 to the n over n squared. Now this is an alternating series, and you can see that it's convergent because 1 over n squared is the p series. So, and the limit goes to 0 there. So now, what n do we need to estimate to within 0.004? So using the above thing, this relationship that we've got here, we can find this out. So we know that our remainder here, this is equal to 0.004, right? And we know that this has to be less than or equal to our bn plus 1. Well, this is equal to 1 over n plus 1 squared, right? So rewriting our 0.004, can write this as 4 times 10 to the negative third. And for the moment, I'm going to set this equal to 1 over n plus 1 squared. And the reason why I'm setting this equal to is because we've got this less than or equal to. So I want to find the exact n that causes this relationship to hold. And most likely it's going to be not an integer. So then we have to back up and think about which direction that we're looking at. But I find it easier to set this equal to find the exact n that meets this standard, and then decide on if we need the integer that's less than it or greater than it, right? So if we do some moving around, we get that 250 is greater than or equal to, oh, sorry, because we're not using, everything's equal now. This n plus 1 squared. Well, this is 5 radical 10, and this is approximately 15.84. We take the square root, right? So that means that n here is approximately 14.811. Oh, sorry, 4. So because we don't have an integer, and n has to be an integer, we go back to our relationship here in green. So remember that this quantity, which is our Rn, right, has to be less than our Bn plus 1. Well, if our Rn is this, and this is the n that satisfies this condition, we're going to need an n that's the next biggest integer, right? So this Bn plus 1 is satisfied, right? So if that's the case, then we have that n must be 15. Okay. So now we're going to start talking about absolute convergence. So if you decided that you were going to take the absolute value of each term in the sum, you would get something like this. The absolute value of A1 plus the absolute value of A2 plus the absolute value of A3, and then so on. Now, if this is convergent, so if this sum is convergent, then the sum without absolutes, so just the sum of an, is absolutely convergent. So this means that the magnitude of each one of these terms added together, if this whole sum is convergent, then we have that the sum that we started with that doesn't have the absolutes is called absolutely convergent. Okay? So let's take a look at our first example. So we have the sum equals 1 to infinity, -1 to the n over n. And we can see that this is an alternating series, right? Just like we did before. And by the alternating series test, we know that this is convergent. Right? So if we look at the absolute values, however, we have the sum of 1 over n. This is a p-series that we know to diverge. So if we have that its alternating form converges, but its absolute diverges, this is called conditionally convergent. I ran out of room. Convergent. Okay. So let's take a look at number 6. So we've got -1 to the n plus 2 power, and then n squared. So take a minute, and then we'll talk about it. All right. So, like above, this is another alternating series. And if we look by the alternating series test, we know that this is convergent. And if we look at the absolute value of each of one of these terms, we have 1 over n squared. And this is a p-series that converges. So together, we have that this is absolutely convergent. So now let's look at number 7. We have sine of n over n to the third. Let's take another minute, and we'll talk about it. All right, so note that this is not an alternating series, right? So we can't apply any kind of alternating series theories to it, right? Because this is not sine pi n, so it doesn't go back and forth between -1, 0, 1, that kind of thing. So just because it's sine n, we're going to have to treat this a little bit differently. So let's take a look first at the sum, the absolute value of sine of n over n cubed, right? Well, the n cubed is always going to be positive, right? Because n is always positive. So I can write this as the sum from 1 to infinity of the absolute value of sine of n over n cubed. So what do we know about this sum? Well, we know that sine is bounded between -1 and 1. What we also know is that if we take the absolute value of this, this is just bounded by 1, right? This is pretty much saying the same thing, right? That the magnitude of this thing is no greater than 1. So if this is the case, that means that the absolute value of sine of n over n cubed is less than 1 over n to the third. And if this is true, we know that the sum of 1 over n cubed is a p-series, and that converges. And this thing is less than that. So by the direct comparison test, we know that the sum of the absolute value of n for n cubed is convergent. So what does that mean about our original problem? Well, we took the absolute value and that thing converged, right? So that means that our original sum of just sine of n over n cubed, this guy is absolutely convergent. Oh, and I ran out of room. Convergent. Okay. Let's go to the next page. That's it. That, and then we're going to be talking about ratio and the root test. So consider the limit n goes to infinity of the absolute value of an plus 1 over an. And we're going to set this equal to L. So what is this? This is the ratio of terms. So the next term, how much larger is it or smaller is it than the term before it? And as we go to infinity, what really happens to this ratio, right? And you can imagine if the ratio is more than 1, that means that each term is getting bigger and bigger and bigger and bigger. And we're not looking good. But we've got some conditions. If we have that L is less than 1, then the sum of an is absolutely convergent. Now, if L is greater than 1, or I should say, or it doesn't exist, or does not exist, and that includes infinity, then the sum of an diverges. And the last condition, if L is equal to 0, then this test is inconclusive. So this test is really nice because most of the time, a lot of terms cancel in our ratio an plus 1 over an. And the absolute values are nice in case it's alternating or it has some kind of negative positive kind of interaction. And then it also gives us if it's absolutely convergent, right? So if it's not absolutely convergent, but it's conditionally convergent, it's going to show up in that inconclusive, right? So L is going to be 0. Right? But we're not too sure if it diverges or not, right? So let's take a look at an example. Number 8. Equals 1 to infinity. We've got negative 10 the n over 4 to n plus 1 times n plus 1. So take a minute, see what you can do, apply the ratio test, and we'll talk about it. Okay. So let's define what power an is. Negative 10 to the n over 4 to the 2n plus 1 times n plus 1. And our an plus 1 is negative 10 to the n plus 1. Now notice that it's 2n plus 1, so if I put a n plus 1 into this, I actually get 2n plus 3 and n plus 2. All right, so our L is our limit as n goes to infinity. And we've got our an here. So we've got negative 10 to the n plus 1 over 4 to n plus 3 and our n plus 2. And then we're going to multiply this by the reciprocal of an to make it a little bit nicer. We have 4n plus 1 times n plus 1 all over negative 10 to the n and absolutes. And this is equal to the limit as n approaches infinity. And you can see that we're going to get some kind of cancellations of this -10 n plus 1 and this -10 n down here. And the 4 to the 2n plus 3, and the 4 to the 2n plus 1, we're only going to get, so the 2n's are going to cancel, and one of those, and the 3 is going to cancel. We're going to have 2 left over, and then we're going to have our n plus 1 and n plus 2 left over. So this is going to be our absolutes. We have -10 left, and on top we have n plus 1, and the bottom we have 4 squared n plus 2. And this is equal to 10 over 16 times the limit, and approaches infinity, n plus 1 over n plus 2. And by dominance of powers, that's going to be 1. So all we're left with is 10/16. This is less than 1. So we're given that this is absolutely convergent. Absolutely convergent. By the ratio test. So, oh, I'm sorry. So there's a question if n is equal to 1. Yeah, that's the inconclusive. Yeah. So I don't know why I wrote 0 there. It's supposed to be 1. That would make sense, right? Because that's the only one that's left out. So now a dumb question. Just a typo. All right. So we've got here an example of the ratio test, and there's another test, the root test. So now I want you to consider we've got the limit as n approaches infinity, square root, not square root, the nth root of the absolute value of an. And we're going to set this equal to L. So our conditions that we had up here are actually our conditions for this test as well. So that's kind of easy to memorize. So let's give it a go. We have another sum here. We want to find out if it is absolutely convergent or not. N equals 0 to infinity. And we've got 5n minus 3n squared over 7n to the third plus 2. And this is to the nth power. Now it's sums like these that root test helps a lot with, because this whole thing is raised to the nth power, and because of the nth root in the root test, this is what makes it so nice. So let's go ahead and start looking at this. We have L is equal to the limit as n goes to infinity, absolute value 5n minus 3n squared, 7n cubed plus 2. And this was raised to the nth power. And then the absolute 1 over n. So the n and the 1 over n are going to cancel, right? So now we've got the limit n approaches infinity of just the absolute value left now, 5n minus 3n squared, 7n cubed plus 2. And you can see that this guy is going to be going to 0, right? So we have that L is less than 0, or less than 1, so this is absolutely convergent. Absolutely convergent. Okay. So the last topic that we have here is getting a little bit into the next section we were supposed to be talking about today, is power series. So what is a power series? Well, a power series is something defined as a sum, and it's got coefficients defined by Cn. So the coefficients are much like a sequence. And then it has x to the power of n. So this looks like C0 plus C1x plus C2 x squared plus C3 x cubed, and then so on. So this looks like a polynomial, and it is a polynomial. But you'll notice there's one thing that's different here than all the other sums that we were looking at before. The fact that we have an x, right? So this thing that's adding up all these terms, well, it has a variable in it now, right? Well, what does that mean? Well, you can write that the sum from n equals 0 to infinity of Cn x to the n is equal to a function of x, right? And we do some kind of analysis, and we're going to see just in a second what we kind of do here, is we learned a lot about infinite sums converging and diverging and absolutely converging and conditionally converging. But what does this mean for this function? Well, this function here might not always be convergent, right? It might depend on what x value you input in, right? So let's put Cn's equal to 1, always 1. So we have 1 plus x squared plus x cubed. That looks like a lot like the geometric series, right? And we know that it's convergent as long as x is between -1 and 1. So that brings us up to trying to find out the radius of convergence and the interval of convergence. So what are these things? Well, the radius of convergence is how spread that a series converges, and the interval is the actual interval of x's that this converges for. So let's look at the sum. And this is the more general way that this is written. So we've got Cn, and now we've got x minus a, where a is a fixed constant. And this is either the power series centered around a, There's a few other terms for it. So there's three things that can happen with this power series. We have that this converges if x equals a. That means that each term would be 0, right? Because we have a minus a to the n, so 0 to the n, and then so on. That's always going to converge, right? If we just keep adding zeros. So that's the worst case scenario. 2, it converges for all x. This is the best case scenario, right? No matter what x we put in, this sum would converge. And third case, it converges for the absolute value of x minus a less than some r. So this r is what I was talking about before as the radius of convergence. How far away from a does this thing converge? And the interval of convergence is actually saying like what range of x's are we looking at. So let's do an example. You can kind of see the radius of convergence and interval of convergence. So we've got the sum here, n equals 1 to infinity, and it's -1 to the n over n to the over 4 to the n. Yeah. So what is the radius of convergence and what's the interval of convergence? Well, a really good way of calculating these things is by the ratio test, because the ratio test actually gives us this inequality at the end, right? And we kind of see that in a second. So let's define what our L is. L is defined as the limit as n goes to infinity. And remember, I'm doing the ratio test here, so I've got -1 to the n plus 1 times n plus 1 all over 4 to the n plus 1. And this is going to be times 4 to the n over -1 to the n. Oh, I'm sorry, I miscopied my notes here. The sum also has this x plus 3 to the n, right? Otherwise, that wouldn't have been a power series, right? So I'm just writing out the coefficients here, and then we've got n, and then we're going to have this x plus 3 to the n plus 1, and then the bottom x plus 3 to the n, right? Well, this is equal to the limit as n equals infinity. And now we've got -n plus 1, because these -1's here, we're going to have 1 left over. This n plus 1 and n, they're going to remain. These 4n plus 1 and this 4n, we're going to keep a 4, and then we're still going to have these, but now we're going to be left with only one of them, because the n's, right? There's n plus 1 of these things, and there's n of these things. So we're going to just have 1 left. So we have -n plus 1, x plus 3, all over 4n. Right? This is equal to the absolute value of x plus 3, because that doesn't pertain to n, so it can move outside the limit. This is n goes to infinity of n plus 1 over 4n. So this is 1/4 x plus 3. Now remember that for this to be absolutely convergent, we need L to be less than 1. Well, this means that 1/4 x plus 3 is less than 1. Well, this means that the absolute value of x plus 3 is less than 4. So take a minute and look at the format of this. This is an x plus 3 absolute, right? So if we look up here, we'll notice that we have that form, right? Where a is now -3. And now we have this r, which in this case is this 4. So our radius of convergence is 4. And our power series is centered around -3, right? So for the interval convergence, this is equal to r. So our interval convergence is -4 x plus 3 and then 4, right? We're just dropping the absolute values and including on the opposite side the negative quantity, right? That's still the same statement, right? So now what we do is we just simplify this. So you get our interval convergence. So -7 x 1 if you subtract 3 from each side. And this is our interval convergence. Interval of convergence. So this power series converges if x is between -7 and 1. So next time we're going to be talking about more on power series, and I strongly suggest making sure you feel really comfortable with this material. I think the next test is going to be the hardest one. Power series definitely trips up a lot of students, and it's why I kind of emphasize feeling comfortable with series once we start getting into that. This is what is the big whammy. So look it over, feel comfortable. If you have any questions, send either me or Dr. Chang an email, and we'll get back to you. So that concludes our recitation. I hope you guys had fun, or at least learned something. So hopefully I'll see you guys Wednesday. So take care, and I will see you guys next time.